Good afternoon, everybody. My name is Charlie Nicklin. I'm Chief Exec of IAgrE, and I'd like to thank you all for joining our October presentation. I'd like to introduce IAgrE Fellow and Chartered Engineer, Professor Bruce Grieve. For the last 10 years or so, based at Manchester University, Bruce has focused on crop sensing and smart agricultural technology. In today's lecture, Bruce will run through concepts and motivations behind the Agri-Sensors Research Programme, covering a number of different technologies. As usual with our lectures, everybody will be muted, and if you'd like to ask questions, please pop them in the chat at the bottom of the screen, and then at the end of the presentation, we'll get you to ask in person. Okay, I'll now hand over to Bruce.
So I'll give a bit of a background to myself. So I've actually been at the University of Manchester now for getting on for about 20 odd years or so. But before that, I was in the real world. I was with Syngenta, the agri-science business. And I am an engineer by background, so I'm not a plant scientist or anything like that. And it was always a bit of the one-eyed man in the land of the blind sort of thing, working in the crop protection business, because obviously their primary motivator is delivering products in crop protection chemistries and in seed genetics. So back in sort of the mid-2000s, they were looking pretty well forward in terms of what else they could do to help the farming community. And so they looked at all sorts of things like enhancement chemistries for crops and the whole sort of nanotechnology area. And one of the areas that they pushed at the time, which they still are, and I think if they were probably a precursor to a lot of companies now going to this, was applying sort of intelligent sensing alongside their products. So they were looking at integrated offers as to what they could do alongside crop genetics and the crop protection chemistries to actually make better products and obviously make more cash out of them. So that was all very well. The only problem was that they didn't actually have an ability to produce these sorts of things. So I ended up as the one-eyed man in the land of the blind, as I say, as an engineer, sat in the business development unit in Syngenta in Basel, looking at these various business offers and what we could do with all these great WYSI sensors and the big roadmaps and all the rest of it. And then we decided, well, we've got to go and do some of this. So that's why yours truly ended up in the academic world, given the opportunity, I think that's probably the best way of putting it, to sort of develop these things within the research community. And for the first sort of 5 or 6 years or so, we were fully funded by Syngenta to actually deliver on sensors and electronics alongside the crop protection stuff. So I'll go through some of the sort of technology platforms that came out from that and how they've sort of grown. But really, where we were coming from was, starting to ask all those stupid questions that engineers have a great ability to do when they talk to plant scientists. But why on earth do you sit in the middle of a field with a notepad? Why are you doing these things? And then go back and say, well, there are other ways of doing this. That's just the way engineers work. So really, what we've been sitting is, and the way it sort of evolved, was that we effectively became systems integrators. So though I'm sat in the academic world, it's very much applied technology. So we probably haven't developed anything which you'd say is fundamental research. It's very much cherry picking bits that exist and repurposing them in different ways. And I'll give some of those examples later. But when you do that, we sit in the middle as an integrator. But we're amongst a whole lot of sort of academic capabilities around whether you're talking about the various engineering and plant science and biological capabilities and that sort of middle corona, but also alongside these enabling technologies that you can actually bring into your systems. I've got to find a better analogy, but one of the sort of best way to put it maybe is it's all very well to make the bomb. It's not, but you need to know why you need to drop it and that sort of stuff. I'm sure there's better analogies than that. But anyway, so you can come up with a new technology and think, yes, that'll do great things to the world or for the world. But you really need to be working with those people that in the know that can actually model the effects of these to see, is it even worth going down that line, or are you actually going to create something even worse than you thought you were going to start with. And obviously in engineering, we've had lots of examples of that in the past about, coming out with the best intentions, but getting a pretty poor result in reality. So we've worked with people at the business schools, it says the Brooks World Poverty Institute there. It's actually the Global Development Institute these days. Sustainable Consumption Institute, all these sort of groupings as to, all the way across the various socioeconomic groups and across the globe as to what is the effect of doing something. And it's been a very fascinating exercise doing that, because then you find out, you need to adapt what you're doing, because otherwise you'll have the wrong effects. And we've worked with outside the Syngenta area. We now work with a lot broader grouping of the whole food supply chain, really, and also into the sort of biofuels end of things. And that's from the private companies all the way through to the government bodies and the NGOs like the foundations. And again, science getting on a bit, but we don't sit on our own. We're not arrogantly sitting on our own here. We've had the various Agri-tech centres now being morphed into an Agri-tech catapult. We work quite closely with that grouping. And we've had the likes of the SCFC, the Science Technology Funding Council. They supported a Food Network Plus. We've worked with the branding at the bottom there is actually, it's slightly out of date, but it's actually the Northern Russell Group universities got together to the group called the N8 and actually worked in this area, not sensors alone, but across the whole supply chain, as to what they could offer. And so if you're looking at the sensors area, that's where we've focused, we're obviously just one element of a far bigger picture. We hear a lot about agri-robotics these days, and we effectively sit as the eyes and ears of robotic systems. So again, we will partner with the likes of Simon Pearson's team over at Lincoln, and with the guys at Harper Adams with the automated harvesting and these sorts of things, to say, okay, well, how can we actually put the sort of front end on that? And of course, everyone talks about AI and machine learning these days. Where we tend to focus is not just around the machine learning aspects, but it's also networked systems. And again, there's reasons why we're doing that, which I'll come on to a little bit later. But one thing that came out very much to me when we were looking with our partners across the academic community, we'd work with psychology, we'd work with nutritional people, we'd work with people up the supply chain, the chemical suppliers, and alongside nutrition, fertilizer sort of suppliers, to say that, the whole food supply chain, farming sits in the middle of that, but it doesn't just stop obviously at the farm gate and pre-farm gate. What we might do in the farm field obviously influences the types of produce that goes out to the consumer, or the types of meat products and the like. But likewise, the consumer then influences back to what you would actually supply, and the sensors and informatics area is a key enabler to that, because of course you can then actually make traceability down the supply chain. So it's I suppose one thing that's come up from this is that you cannot sit just in the farm field and think, well, we're doing that for monitoring this weed growth, and we're reducing the amount of potential contaminants into the supply chain. There's a lot more than that can happen down that line as well. So why is this happening? There's been various academic reviews as to what's happening in the industry. This one was done by Harvard it's getting about 10 years ago now. And they started with, well, the agri supply chain started with products, sitting there with a tractor, as they would do with a bunch of economists working on agriculture, and then realised that smart products happen. You put a bit of intelligence into your tractor, and then they start connecting them. And of course, when you start connecting things become a lot more interesting, because then you don't just have your tractor being smart and talking to other tractors. It talks to all the farm equipment as well. And what then happens, as these guys were pointing out, is that your whole industry then starts linking up. From your weather systems providers, seeds systems, irrigation systems, and companies start forming around that. So a whole series of companies have now got, I suppose, an intelligent element to them. I know with the the agri-tech companies, sorry, the agri-business sort of companies, the Syngentas and BASFs of the world, which tends to be where I sit in the domain, they all have their own sort of apps and intelligent farming sort of capability that goes alongside the products now. And these become separate businesses. So that's very much driving home. But what also happens is that obviously where this is potentially making money in new ways, the venture capital industries get involved, and you start getting a whole series of startups forming around this. And we've managed to actually take advantage of that. And then we're now finding the big companies are getting involved when they start seeing the tech companies, they start hoovering them up. So we've been working with the likes of Sony recently in terms of one of these products, and it's nice to see the big electronics companies now waking up to the idea that agriculture is intelligent, and there's a lot that they can do, that rather than just flogging mobile phones or technology around that sort of thing, that there's specific products they can generate in that area, which is a wealth creator both for them and actually hopefully for the industry itself. So I'll just give some. Okay, I've got a quick slide here as well why this is actually happening. We all hear about climate change. We hear about the obviously you've got the likes of labour costs going up. We've got the ageing farming population. It seems to be it's not a UK thing; it's a global thing. So availability to labour is becoming more of an issue. We've got security of supply issues, and we see that globally. It's not just Brexit. And we've got obviously I put there fickle consumers. I think it's consumer preferences becoming more intelligent. We've seen a big shift now recently into sort of I suppose more vegetarian, more vegan sort of diets, with understanding all the effects of different diets on sustainability. And around that, you have sort of enablers. You've got the robotics and automations becoming cheaper. We've got machine learning it's becoming endemic now. Consumer electronics, the sort of components in consumer electronics, again, very cheap, but also very easy supply. And then we've got the whole connectivity of the world. So that's driving the industry along quite a bit in terms of the types of products. In particular, we're seeing with the sensors end, a big shift from what was done in the laboratory in the past, now being done in the farm field, because you do have that additional sensing capability. And in a laboratory, you might have used a mass spec or a gas chromatograph or some other piece of nice stainless steel equipment to get some measurements. What we find certainly in now that we've got intelligence on the sensing systems is that you don't necessarily need the most intelligent sensor, so the most specific sensor in the world. You don't need that massive, great piece of laboratory equipment a lot of times if you have a lot of sources of information which might have more noise on them, because that noise will then be corrected. And that's why network systems, when you could actually have a load of information coming into a single repository, is so powerful these days. And it opens up that ability to get real-time measurements, I suppose just-in-time sort of measurements. So that's a definite transition that we've been seeing over the past 10, 15 years or so. And that brings us through to all the other end of things, where the just-in-time manufacturer, there's now an agri industry 4.0, it's really 5.0 now, trying to apply similar techniques to farming production. Obviously, we're going to have the vagaries of the weather, no matter what happens. But you can control around those and trying to apply those sorts of policies about just-in-time manufacture into crop production. In particular, of course, with the controlled environment production, that's a lot easier than the field. But there's still things that can be done in the field as well. So to give some examples, I'll just give 3 areas that we've certainly worked on, which hopefully resonate with some thoughts about where other people are going. But just to give a feel for the sort of area that where we've driven from in this area. I worked with a German academic a few years ago, Lutz Plummer, and he made a comment here. I've got a phrase. I know you English people use this phrase, and I think it sums you up. Right, what's that then? Cheap and cheerful. Right, thanks for that. So what this was basically was, it's always been working on the basis of cherry picking technology that exists. And an example of this is what we started doing probably about it's probably about 15 years ago now, and that's around active multispectral imaging. Now, I take it that most people on this in the audience will know what multispectral imaging is. We obviously see a lot of it with satellite imaging, getting the nice NDVI images of where the foliar composition is over the globe and over nations and the like. But there's a lot more that can be done than that. So basically, briefly, so multispectral imaging is taking every pixel in an image and looking beyond just the red, green, blue measurements that we see with our eyes and breaking those up into the spectra behind them. So typically, there's lots of effects that can come from that. And there's lots of information that comes out from that. But typically, that's been done with passive systems. So the sort of systems that will be sitting up on a satellite or sitting in an aircraft flying over fields, or even on a drone system, is basically a very sensitive detector with a set of filters in front of it. So the effect of that is, of course, you take all that sensitivity of the detector and you take away 99.9% of the light it's receiving and just filter out the various bits that you want. So we worked, we're not the only people doing this, but we worked with a team over in Bonn University, and they were the first guys that we'd seen looking at multispectral imaging, but close up to a plant. So it wasn't looking at, from at the field level, it's actually looking right down to the leaf level. And the way they did it was with this sort of kit that you can buy off the shelf for about 150,000 euros. And this is a multispectral camera here. And they bolted it about 2 meters above the plants, and they lit them with these halogens, which is all very well. But what was happening then was that the halogens would basically burn the plants, the amount of energy they're putting down. But they had to put that much energy down to be able to get a good signal to noise on the detector. So we basically just said, okay, we'll turn the problem around. And we turned up with, I think it was something like a $300 digital SLR camera, and it was probably about 2 megapixel one at the time or something, whatever we used to get it about 15 years ago, and 1,000 LEDs, and so that was basically a therapeutic afternoon spent with a research associate actually putting these onto a PCB, and they'd generated models at various wave bands for a particular disease. It was actually Cercospora disease on sugar beet. And they'd been using their high definition camera on that and getting these models out about the early ingress of the disease. So we turned up with these LEDs and a camera, and we got better signals than they did for about an order of magnitude less cost. And so this is actually the sort of thing you get. It's a sort of false kind of images of where the Cercospora spores are on the leaf. So what I'm trying to say here is that the reason we got those better images was because we'd turn the problem the other way up. We'd actually put a lot of light intensity down exactly the wave bands required. So you didn't need to burn the hell out of the plant, but you got good measurements, and also we got a high definition image because our digital SLR camera actually had a higher resolution sensor than the official kit with its filters in front of it. So from that was all very nice. You can actually start getting measurements at a lower cost. There's also with a single camera, what you can do. We started working with the University of West of England at Bristol, and so they've been using a technique called photometric stereo. And so basically, that was exactly the same LEDs that we've been using to light the image before. And but all you do then is you basically turn on and off which LEDs you're lighting, and you get a three-dimensional information. It's basically like imagine a spotlight lighting something on the ground. You get shadows forming around it, and that's effectively how the technique works. So really, I suppose what I'm coming from here is saying that there's some clever software behind this, but the actual bill of materials, the actual component cost is actually very low to get three-dimensional information. And you also can get not just multispectral information, but you can get fluorescence information as well. I'll come on to that briefly later, but maybe just give an example of the sort of things we were doing with this stuff. This is a project we did with Harper Adams and Syngenta and G's Fresh a few years ago now. This on the back of here is a unit which it's designed for spot spraying weeds as you go through a field. And so we took our multispectral imager, which is basically sitting under our multispectral imager, and popped it underneath the unit here. And so that was alongside a little an array of valves, which the idea being that we can actually start doing applying non-selective herbicides to the crop, not to the crop, to the weeds around the crop, and getting around all the issues about selective herbicide tolerance. And again, obviously, people have been doing quite a bit around this with image processing in the past. But while we came at it was by using the multispectral imaging, we managed to actually start doing measurements with false color images, just using basically 2 or 3 bands. And we got a very high speed measurement to be able to pick out exactly where the weeds were amongst the crops. So, you know, if you start looking at the sort of washing machine vision here, the processing actually can pull out very, very, very easily using multispectral imaging. And that was, again, just using a few LEDs and a couple of cameras. So very cheap and cheerful stuff. And from that, we actually span a company out, which are now, I think they're now about 6 years into development and producing products, and I think they're doing quite nicely actually. That's an ex-PhD of mine. So yeah, there's actually economic value that comes out from these things as well. But alongside the work in farm fields and that sort of thing, we're also working with the developing economies, and in particular, we work with East Africa on cassava. And this is, again, applying the same multispectral approaches we had in the back of that tractor into a little handheld unit. And the bill of materials on this is at the moment about £200. We're trying to get it down to less than $100. And what it's doing is basically picking up viral infection, pre-visual cues of viral infection in cassava. Now, cassava in East Africa is it's the main carbohydrate source in East Africa. And it's affected, its yield limited by 2 viruses, brown streak and mosaic virus. And as it sounds, yeah, they make that patterning on the leaves, but you only see that when it's too late. And it's a tuber which is basically propagated via cutting. So of course, if you get the virus going along from one cutting to the next, then it'll spread, and there's a sucking pest, whitefly, that actually spreads it further. So it's a case of, there's a lot of parallels to COVID here. You know, you isolate and eradicate, and so we're working on these little bits of kit alongside the International Institute of Tropical Agriculture and some colleagues in the US to get these things deployed into the supply chain, so as to start eradicating the disease in East Africa. So, you know, it's from one end to the other, but it's the same, you know, from tractor to little handheld units, these little network GPS handheld units, and it's a universal platform effectively. That's what we're aiming at. But it's all the same thing. It's all a camera, a few LEDs. So nothing dramatic about that. And what you can also do with it, and we're working with colleagues over in Sheffield, so there's a lot of partnering on this with the plant science community, is we're doing a thing called periodically modulated fluorescence with the same technique. And this is basically looking at the photosynthesis mechanisms in leaves. And you get some fascinating results because, of course, photosynthesis drives everything in the plant. And so things that all the diseases, all the abiotic stresses, all the nutrient stressings, and all the likes of saline and water stressing, all these sorts of things, they all start forming distinctive patterns in the way they're shutting down the photosynthesis mechanisms and the Calvin cycle underneath. And by this sort of complex looking graph is basically what comes out from behind every pixel in the image. And what I'm trying to just sort of depict in this very complex sort of set of images is that if you imagine a plant responding to light, it'll turn up its gain and turn down its gain, so to speak, in terms of the amount of light that's around. It's got lots of protection mechanisms if it's too bright a day, and then it will up its sensitivity if it's a dull day. So if you modulate the light very slowly, the plant will try and follow that. And if you start speeding it up a bit more, it can't follow it anymore. You start shutting down reactions in the plant. And you can see those because it refluoresces. So every pixel in the leaf is giving a signature of how the plant is responding. It's a fascinating world, and we're really just trying to understand what the plants are telling us. It's almost like talking to plants with light. So that's again exactly the same piece of kit. It actually does it. Just a camera and a few LEDs. It's amazing what you can do with a few light sources in the camera. So just moving on, sort of conscious of the time. So a second platform, if you're doing clever things above the plant, where we've gone is also cheap and cheerful below the plant. And this is using a technique I refer to as plant to plant. Because if you talk to most engineers about a plant, okay, maybe agricultural engineers might be slightly different, but most, a chemical engineer would think a plant is a big steel thing that makes chemicals, whereas of course a biologist would think of a different thing. So we've actually translated technology from the chemical industry, and this is actually a set of electrodes in the bottom of what we call a pressure filter, which separates solids from liquids. And these electrodes basically inject small currents into the slurry in the base of the pressure filter. And what these things were doing originally was doing a safe method of imaging what was actually happening as far as the liquid separated from the solids in the filter, and actually how it distributed itself, and making sure it's all even. So we basically said a bit of a mind leap, saying, okay, well, the pressure filter is all very nice, but a soil is effectively a filter. It's a very complex media, but it's effectively just acting like a filter for the nutrients going through it. So you can apply the same techniques there. So we put a load of electrodes around the soil and started reconstructing images from those, because you can do that by driving small currents through the electrodes, measuring the voltages around all the remaining points, and if you move these around, you can start building up an image of what's happening inside there. So if you start looking at plants under the underground, obviously it's like icebergs. Most of the things on plants are happening below the ground, not above the ground. And this, so we started looking at a disease called clubroot in brassica. And so you can see the effect of clubroot forming in these images. But above the soil, you don't see a lot happening until this happens, and then this lot dies. So you really want to be seeing what's happening below the soil. And so that's what we started doing with these, just a set of electrodes with currents being driven into them. Again, clever software reconstructing the images, but it's very cheap to produce. We've got a couple of little circuits here that probably we can knock these things together for about 50 quid these days. And this is a bigger, older variant of the unit, but the whole thing's scalable. And so we work alongside people like the Hounsfield unit in Nottingham, where they've got these massive great X-ray machines, which are all very impressive, producing these very high definition views. And we come up with our little electrodes and get nothing like the level of definition they get. We get sort of what we call blobology. Basically it's the image reconstruction is nothing like the same quality, but you can actually reference what you're trying to see using these sort of X-ray techniques, these hard field tomographies, and then apply the cheap ones more ubiquitously. So we've been doing this, we've got our colleagues over from Nigeria here, so we've been doing this on things like phosphate monitoring and soils, and monitoring that sort of the uptake of the root structure in that. And so from doing that, of course, you can start saying, well, why not link all these technologies together? Start looking at what you can do above the crop and what you can do below the crop. And so this is what we're starting to do in the large-scale laboratories at the moment. We've got a setup in South Manchester now, which is basically a robotic system with a set of monitoring units under under the plants themselves. We start to get simultaneous measurements of what's happening above and below the soil. Use again these cheap techniques, and these are sort of things that we're looking at now at phenotyping. You know, what we can do in terms of breeding technologies, but also more recently, we've been working with there's a research council call on protected and controlled environment farming, basically controlled environment production. And so we're setting up a demonstrator unit in what we call the Reynolds Building in central Manchester, showing how we can actually get this technology to both help with the recipe development for plants being grown in these sorts of environments, but also trying to work with the local communities. So a lot of the I suppose everything from the using politically correct terms, the lower socioeconomic groups to the very wealthy sort of consumers, saying, well, what types of crops would really make a difference to you if they could be produced with the right flavour traits and the right organoleptic, the right sort of features. What beyond just the usual leafy greens that are grown in these? What would you want, and what would you need from them? And actually using these sensing technologies to provide that. So the reason it's sat in the city centre now, so we can actually get the communities involved with it. So coming on to a third technology platform, and I'll close out the next few minutes for questions in the lab. So it's all very well looking above the crop, below the crop, and a lot of times looking for stresses which are coming from diseases. What we'd also like to do is pick up those diseases before they even hit the crop. So we've been working, this is where we do work with the likes of Sony, on understanding what the spores, the various disease spores, is actually doing on the leaf itself. And so when we've been doing this is basically attempting to trick nature. So I'll just run this in the background. So basically, we've been working with Sony and actually some of the foundations on little sensors that sit in the field, and what they contain is a material which basically mimics the plant leaf. So spores, when they land on leaves, or on livestock for that matter, they're very selective. And this is a problem when you get a CGI person getting involved with spores, they sort of make it look like the alien. But they're very selective as to how much energy they will dissipate. They're like a little battery inside them. They've only got a certain amount of energy, and so they will not bother expending that energy unless they're pretty certain they're on their host. So there's a lot of trigger mechanisms in spores to say, are they actually on the host? So those trigger mechanisms you can trick with appropriate materials engineering. So what we've been doing is developing materials which effectively mimic the plant leaf. I can't go into detail about how they actually operate, but they are just basically clever materials. And if you pop underneath those imaging sensors, then put them on a network, you can start getting a grid of sensors that tell you in real time, not just that you've got spores in the field, because spores in the field, you might have it all the time, but they are actually active and doing something. So we've been working alongside, originally it was the Gates Foundation, looking at wheat rust coming into East Africa. And more recently, and we're still working with the Gates, but more recently it's actually developed into the UK farming alongside a DEFRA proposal, which is now it's about a couple of years into its development. So we're working with NIAB in Cambridge, working with the Sony guys, working with BASF, in terms of developing these early indicators for rust in wheat, but also now working with G's as well for looking at downy mildew in lettuce. I think it's I think spinach, and what's the other one? We've got it's also spring onions as well. So again, looking at a portfolio of different diseases, make up like almost like a universal disease sensor. So picking up the disease before they even hit the crop, where your multispectral imaging and your likes of the root imaging would actually pick these things up. So alongside that, there's some clever engineering going on around the optics as well. And so we're looking at things like lensless imaging, not even having a lens on the camera, because that's quite a high cost item. Even a little acrylic lens is relatively expensive. Because if you want to make a precise one, it adds to the cost of the camera. So just take that bit away. So look at the likes of using our light sources to actually create holographic images as well. So basically, I suppose to close out, I mean, where we're sitting on this stuff is effectively acting like the eyes and ears of robotic systems. So it's all just one part of the picture, and we're just infilling alongside a lot of other people some elements of that. So I think I'll probably close out at that point if that works with everyone else. Oops. I think that's the end of it. I'll stop sharing.
Excellent.
Very much.
I'll kick it off. Where do you think this sort of tech is going in terms of, because obviously you've seen, you see visual and sensing techniques on board machinery for spot spraying or mechanical weeding, that sort of stuff, and then obviously the below the ground level stuff is ultimately static, isn't it? And if it's an infield on farm, then the below ground is clearly very specialized. Where do you sort of see that stuff going? Are you trying to find a route where you can do this stuff above ground and it stays mobile?
Yeah,
and trying to get that technology cost effective to go onto machinery so it doesn't become more specialist, if you know what I mean.
Yeah, I mean the above ground stuff. Part of the reason it's more deployed than the underground stuff is because you can stick it on a toolbar of a tractor or stick it on a drone, something like that. The reason, the stuff we've done below the ground so far always suffers from that thing about, you've got to have a set of electrodes around the unit. I mean, with the technology we've been using, a colleague of mine is actually working on things like ground penetrating radar, which you could drive around on a quad bike and the like. But it doesn't give you the same level of selectivity. And we've thought about all sorts of things, right? Especially things like potato production, looking at the tuber growth, where you could actually around the sort of raised beds where the potatoes are growing, you could put electrodes around that. It's always been a struggle to see how that would actually work in reality. I suppose no-till production actually helps in some ways. You could actually imagine a situation where you effectively create a grid of electrodes. I mean, electrodes themselves are very cheap things, and no-till wouldn't plow up across the area that you've got your electrode systems or your controlled traffic farming type approaches. In reality, where it's been sitting so far is in the likes of the phenotyping world, where you're actually trying to just look for features in big screens of crops. And there you can actually have just well interconnected big glass houses, or the controlled environment farming, of course, where you can actually have the trays kitted out. And that's where we are working at the moment. I suppose in reality, what's going to happen in the field is ideally you get a model that links what's happening above the crop with what's happening below the crop. So you wouldn't necessarily have to monitor every single plant in that field. You get almost like a proxy from looking what's above it. But yeah, it's always a struggle that below to above. But the ability to measure things at the same time, above the crop and below the crop, that is, to me, that seems a big growth area, because so far we've had, these massive great X-ray machines which do a superb job, but you only have a few dozen of those things spread across the country, if that, and then you've got a lot of work being done on the various imaging approaches above the crop, and some of them are very high definition, but the two don't sit in the same place. And so you're only getting measurements, one measurement or another measurement, and you've got to move your plants to the machine rather than the other way around. So the ability to have these things available everywhere is a big driver. Dropping the cost and actually getting these things out there is a big driver, as far as I'm concerned.
Yeah, yeah. And I suppose you mentioned controlled environment, which most people immediately think vertical farms.
Mm.
Then you'd call a glass house a controlled environment, wouldn't you?
Absolutely,
And
yeah.
and you've got soil in a glass house, and you could have stuff permanently buried in there, I guess, because it's
Mm.
more controlled than perhaps your average field.
Yeah, I mean, if you look in a glasshouse environment, a lot of them are spectrally enhanced anyway. You know, that even during the day they'll have some enhancement to the light with LED lighting, and obviously at night they'll control those. But there's no reason the technique shouldn't work. You just back off the effect of the daylight. I mean, it's not ideal. You know, you ideally want a dark environment if you're doing multispectral imaging, but you can actually operate them at least in subdued light. My colleagues over in photonics, they're actually working a lot now. It seems a bit odd, but they send the robotic units out at night, you know, or at dawn and dusk, you know, so they've got subdued light anyway. So you obviously can't do that for all features because the diurnal effects of plants during the day, you know, they'll change their responses during the day. But if you know there's certain things you're looking for and they do express themselves in subdued lighting, you just send the units out in subdued lighting.
Yeah, yeah. Oh, that's interesting. Yeah, okay. Toby, you have a question? Do you want to unmute yourself?
Yeah, just I was just thinking of the spore detection system. Is that very specific to one wheat rust? How difficult would it be to develop for other crops, pathogens?
Yeah, we're trying to make a generic technology. So you know, it's a cartridge that goes in there. So the imaging units and the type of lighting and the networked comms that go underneath it are a shell. So that would be universal. The cartridge that goes in there, the material is specific for a particular disease. So, you know, for the rust, you know, we've been looking quite a bit with the now folks in terms of what are the cues that actually make rust germinate, and in particular yellow rust, because brown rust and stem rust, they'll germinate in slightly different ways, and so we're making it specific for yellow at the moment. But the idea being that you could then, I mean, the mechanics of that particular unit, and it literally is like a cartridge. It's got a little stepper motor in there, and it'll spin around the sensor assembly, so it can actually go to different sensors. The issue that you know the obvious fly in the ointment is that once the sensor's used up, then it's used. You know, it's a disposable item. So if you're going to have multiple diseases, you might only have one or two sensor elements that actually pick up a specific disease per cartridge, and so your cartridge gets spent quicker. You know, if you imagine you've got say 12 or 16 faces on the thing, and each one does one disease, or you know you have six that do the same disease and another six that do that same set of diseases. You've only got two bites in it before you kill the thing, and every disease phase coming through will kill it.
Mm.
And by kill it, I mean you just have to send somebody out to actually go and replace the cartridge. But you know, it's a pain to do that. It'll know it's dead, but you still have to. That manual bit of having to go out and do something with it is still going to be there. So the reason we've been working on one disease at the moment is partly just to keep focus, but also it's got enough spare elements in it that it could run easily through a season without becoming spent.
Mm. I was thinking of an application for Esther Kimani, who won the Royal Academy of Engineering Africa Prize this year. She's got a fairly robust business using cameras for crop detection, and she's looking as to what else she could do that would be in advance of the crop actually wilting away.
Okay.
So that's something I might talk to. I'll ask her if there's a few specific diseases that she's really interested in.
Yeah, I mean, maybe send the link to us. Yeah, I'd be interested.
Yeah, well, she's certainly very dynamic. I think we interviewed her recently when she came to London to accept the prize. So yeah, I'll have a chat and see if there's something that we can take forward.
Yeah, it's all about networking anyway when it comes down to it. Okay,
Yeah, yeah.
Okay, any more questions? I think Declan is yours. I presume that's more of a comment. Just reading it on my screen.
Yeah, I'll just say that was fascinating, jaw-dropping presentation. Unbelievable where you guys are all going. So as Charlie was saying, underground is tough, but it could be for experimental work, and it still could be really useful for experimental work. And but I think farmers most likely have the biggest problem with crop disease. So to save farmers money, having these sensors out in the field that detect spores early on would be a huge benefit. And I don't think you would need that high density of these sensors, because if you were in Cheshire and you get one spore in a sensor, you know that disease now is in the UK. So I think it's a fascinating that example number 3 probably has lots of legs, to be honest with you.
It's an interesting one when you look at the value capture, especially when you work with the crop science guys, because you take something like BASF, their business is based on, well, I suppose it depends how they define it, but they want to flog chemicals, and of course you're going along saying, okay, we haven't got a disease, you don't need to spray. It's cannibalistic in some ways on their business, but it's that then you come around to, well, it's not about just flogging chemicals. It's about actually the final effect is generating more yield because you've got less disease. So the way we've been working with the crop protection guys is saying, if you know exactly when it's occurring, obviously the chemistries are designed to have a limited fate. Basically they're all designed now to disappear, and so they're only active for a certain period. So what you don't do is spray on program. And actually get the point where the chemistry is dying away and it only has a minor effect. What you want to do is know exactly when the disease is actually becoming active, and then hit it with well, in that case, if you've got a curative, obviously that's a good option. But also, if you've got a preventative, then you need to know that the disease is coming into one area, and all the models, it's ground truthing the models that then say it's heading your way. Get your preventative down now, because that'll have the greatest efficacy. And that then hits another interesting business model is the person that makes the money out of it is then the farmer, because they've got more yield. So how do you get value capture back to the guys offering the service? And that's what you end up with. It's not just about the engineering, it's about all the financing around it. Fascinating world.
Yes, yeah, I'm seeing it from the farmer's point of view. I'm not seeing it from the big chemical companies' point of view. But
whoever provides it, even if it's an electronic company or whoever, everyone needs to make some cash out of it from the overall win that comes.
Yeah, well, fascinating talk. I've learned so much. Thank you.
Maybe the cynic in me. I read the other day that BASF are pulling out of agriculture, aren't they? So have they recognised this long-term future or lack of with chemicals in agriculture and decided to get out before it gets too tough? Maybe, I don't know. That's the cynic in me.
I don't know. I suspect they're probably going in more into the out of the chemistry, but actually having still the bio effect and all these sorts of things. Yeah. Anyway, I don't know what BASF are doing, I must admit.
The other thing I suppose is with the third exemplar is I suppose that's one bonus of having monocultured crops, is that if you put a sensor in the middle of a wheat field, there's not a lot of other things interacting with it, is it? It's quite densely populated with one crop.
It certainly becomes easier like that. But I say you can have multiple diseases in the thing, and it basically does ground truth the existing models. It's not like we're coming along saying this is the only thing. If you've got a wheat field sat amongst rape and barley or something like that, the models will say, okay, you're likely to have these types of pathogens coming into your field. So that's all it's doing, is basically saying, yep, it's true, and it's happening now.
Yeah, agronomists will be able to work from home soon.
Well, yeah, absolutely.
they'll just get a message on WhatsApp saying such and such down the road has got this disease coming.
Absolutely.
Picked it up.
Somebody's still got to go out there and actually have a look at it's real, though.
Yeah. Okay. Toby's mentioned, is there a paper he could reference on the spore detection system? I don't know if you wanted to pick up with that separately or.
I think the Leslie over in NIAB's in the process of writing one at the moment, so it's not out yet. Partly because there was a lot of IP that was also being generated around it as well.
Okay. So thank you for being a stand-in, because obviously it was a bit last minute getting you arranged. So thank you for that. And a really interesting presentation. Very, very interesting stuff. So it's very much appreciated. So thank you everybody else for joining, and hope you'll join us for our next lecture, which is on the 12th of November, where we'll be joined by Dr. Mark McBride Wright, who was previously scheduled, but he had to pull out due to ill health. Mark's a recognised diversity and inclusion leader, and he's going to be talking about that particular subject and STEM. So that's it should be an interesting presentation. So thanks again, everybody, and we'll see you next time. Bye-bye.